Okay, so time for some half-life. Half-life is actually a huge concept that's used in a number of different areas in chemistry. We're going to be talking about it in terms of kinetics and how fast reactions are taking place and whatnot. And we just finished talking about, first order reactions, second order reactions, and the time it takes for the concentrations to be, decreasing. So half-life is going to relate to a really, really specific scenario. And you can see the symbol we use for half-life is a T with a little half symbol as a subscript. Oops, sorry about that. Okay, that's over. Right, so it's a T with a little subscript, like so. And that symbol means the following. What half-life is it's the amount of time it takes for half of the original initial concentration to react, to go away. So it's a really specific scenario of how much time does it take for half to decrease. It has a lot of application in nuclear chemistry. We're not getting into that right now, but they just want us to be able to apply this idea of half-life to first-order reactions. It gets much more complicated with second-order reactions, and therefore the curriculum just calls for us to understand first-order reactions. Now, I'm going to give you the equation for half-life, which is actually an extremely simple equation, but I want you to see where this equation was derived from. I want you to see where it came from, just because it gives you application outside of this. You don't have to learn this. I'm not going to ask you to derive it, but I do want you to see why the equation ends up being what it is before we actually look at the equation. So, as I told you before, which is for first order reactions. So you see your first order time equation that we have learned before. And I don't know why my T is missing from there. So there should be a little T1/2 on there. I think it's on your paper. For some reason, it just didn't show up on my smartboard. And so that's your equation for first order problems. Now, in terms of half-life, we said you have some initial concentration, and when half of it's left is when you're at your half-life. So I'm going to call the initial concentration X. Okay, so right here, you can see I plugged in X for my initial concentration, and then I plugged in 0.5 X as my final concentration, because we're trying to calculate the time it takes for half of it to go away. And so I plugged in those values. Then if I rearrange a little bit, I don't know if you remember from your math class, but when you are subtracting two natural logs from each other, it's the same thing as doing one natural log of the first one over the second one. Okay, so it's just sort of math rearrangement of equation. So we end up with this one equals K times your half-life. And then when I solve, so I cancel my x's, so I do 1 over 0.5, and I take the natural log of that. So 1 over 0.5 is going to equal that. Well, 1 over 0.5, when I plug into my calculator, is 0.693. So 0.693 equals K times your half-life. So if we rearrange, you see that the equation for half-life, T of 1/2, is just 0.693 over K. So this is another way that we can calculate K and figure out K, was if we were to know what a substance's half-life was, we wouldn't even have to be given concentrations. Doesn't matter what they are. It doesn't matter if you're starting with 0.1 and going to 0.05. Doesn't matter if you're starting with 0.5 and going to 0.25. It will all mathematically work out to be the exact same amount of time. No matter what your initial concentration is, it will take the same amount of time to get to its half-life. So it's a very, very simple equation. You see, it's just a two-variable equation. But I wanted to show you where it derived from. All right, so let's go ahead on to example problem number 1. So for example problem number 1, if you take a look here, we have an equation, okay, which we don't really need the equation. I say really, we don't need it at all. What we do need to know is the fact that they're telling us that it's a first order reaction, okay, because that means that we're allowed to use the half-life equation. We've got a rate constant given to us right here. That's K. We've got a temperature given to us, but if you think about the equation, we don't need temperature, okay? And they want us to calculate the half-life. So they want you to calculate T1/2, all right? So the equation, again, T1/2 is equal to 0.963 over K. So I know what K is. So T1/2 is going to be 0.963 divided by 5.336 times 10 to the -4th. and I'm going to solve, and when I solve, I end up with unrounded this value, but we want to round to our sig figs, so I've got 3 in my k. That's the only number I used, so I want 3 in my final answer, so it's going to round to 1,300 seconds, 1,300 seconds. And it literally is as easy as that. So if you are given a half-life, or you're asked to calculate a half-life, and you're given k, or vice versa, it's a 2-variable equation. It literally is just plugging it in and getting your answer. Now, you could go back and use the ln of the initial concentration and the ln of the final concentration equation and just plug in x and 0.5x and solve. You'll still get the same answer, but there really is no reason to do that. I mean, this equation makes it much simpler than that. And this equation is listed on the equation sheet for the AP test. All right, let's go ahead and take a look at the second one. So this one says we have the thermal decomposition of this compound into its elements, and they tell you right here it's first order. You need to read problems, okay, because they're going to give you information often in the context of the question. We don't care about this. It makes no difference to us whatsoever. They tell us the half-life is 35 seconds. So they're telling us what T1/2 is. And they want us to figure out the value and the unit for the rate constant. So again, our equation, anytime we're dealing with half-life, is going to be 0.693 over k. It's going to be your half-life. Now this time, they've given us the half-life, so I'm going to plug in my 35 seconds here. 0.693 over k. Cross multiply, and you end up with a k value, rounded to 3 sig figs, of 0.0198. Now, here's the deal. We need to figure out what the unit is, okay, because it said the value and the unit. Now, you know that if something is first order, then its unit for k is 1 over time. And in this problem, the time is given in seconds. So your unit is going to be 1 over seconds, just like any first order reaction will be. So it really is as straightforward as that. Again, take a look at how the equation was derived, because it can be very useful in other contexts to use that idea that we did in there. But the equation itself is simple enough to just be using by itself.